Greetings and welcome to online lecture 6 on unit number 2, that is fluid statics. This lecture we are going to discuss the numerical on hydrostatic forces. Previous lecture we have discussed the theoretical part, that is the derivation part, how to estimate the expression of total pressure and the distance of Cp from the free liquid surface. Initially we have discussed the expression on inclined plane surface. The expression of total pressure for three cases, that is inclined plane surface, vertical plane surface, and horizontal plane surface remains same. That is F is equal to gamma AX bar. That expression is used for these three cases. And the expression of H bar, that is for inclined plane surface, first it is derived, and based on that, by putting the value of theta for 90° in vertical plane surface and theta for 0° for horizontal plane surface, the H bar relations are obtained. So these two relations only we have to use for calculating the total pressure and H bar, that is the distance of Cp from the free liquid surface. Basically, there are some mechanism, engineering mechanics principles are also used while solving this problem. So these are some expressions. The common shapes appear in the problem, that is a triangle, square, circle, rectangle. So as far as the triangle is concerned, so the area of the triangle everyone knows. So we have to memorize these expressions. So the area of the triangle 1/2 BH, 1/2 BH. Then the moment of inertia about Cg. So this is required, moment of inertia about Cg. In some cases, moment of inertia about base is also required, but most of the cases, the Ig stands for moment of inertia about Cg. So whatever the expression of H bar, that is Ig term is there. So for that, it is required. So as far as triangle is concerned, it is 1/36 BH cube. For rectangle, it is 1/12 BD cube. So B is the surface, or the it is the edge which is parallel to the free liquid surface is generally considered as B, and the edge which is perpendicular to the free liquid surface, it is generally considered as D. So whatever will be the orientation, so the edge of the surface which is parallel to the free liquid surface, consider it as the B, and the cube of the edge which is perpendicular to the free liquid surface. So BD cube. For circle, it is pi/64d⁴. If it is a half circle, it is pi/32. So, like that, these moment of areas are considered. We can say moment of inertias. This surface is rarely used, but you have to memorize this expression of at least these three for solving the numerical. Straight away, we go to the problem. This is a practical oriented problem. A heavy car plunges into a lake during an accident and lands at the bottom of the lake on its wheel. So this is a situation in the lake. Total depth of the water in the lake is 8 meters. 8 meters is the door is 1.2 meter high. So the door height is given, that is 1.1 meter wide, and the top edge of the door is 8 meters below the free surface of the water. Determine the hydrostatic force of the door and the location of the pressure center, and discuss if the driver can open the door or not. So the practical situation, sometimes it happens. The depth is 8 meters. So whether the driver to able to open that door or not, or if it is, then what force is required to open that particular door and where that force is to be applied. So this is actually the situation. So again, a car is submerged in water and hydrostatic force on the door is to be determined, and it likelihood of the driver opening the door is to be assessed. Opens the door, so that is from the field. So first assumptions that the bottom surface of the lake is horizontal. Then second one, the passenger cabin is well sealed so that no water leaks inside. Number three, the door can be approximated as a vertical rectangular plate. So we consider this case as a vertical rectangular plate. The fourth assumption is that the pressure in the passenger cabin remains at atmospheric value since there is no water leaking inside. That's why. So we can use the formula of vertical plane surface. So for total force or total pressure, that is F is equal to gamma A x bar. Now we have to recognize the expressions. So that is gamma in this case, and this is water, it is 9810 Newton per meter square. Area of the door, as the rectangle door is there, its height is 1.2 and width is 1 meter, so 1.2 meters square. And x bar we can calculate. So 8 meter plus the half of the door height. So door height is 1.2, its half is 0.6. So 8 plus 0.6, 8.6 meters. So the total force that is exerted on the door from the outside, that is 101.39 kilonewton. So that is the pressure exerted at the center. Then its location, so where that pressure is acting, so that is calculated by uh, the calculating the distance of CP from the free liquid surface, that is H bar. So where that force acts, so H bar is equal to, as this is a vertical plane surface, for expression of H bar, that is equal to Ig upon Ax bar plus X bar. So Ig, as it is a rectangle, is 1 by 12 BD cube. Obviously, BD is the width that is parallel to the free liquid surface. So 1 meter is B and 1.2 meter is D. So Ig we can calculate, that is 0.144 meter raised to 4. So finally we can calculate H bar, that is 8.61 meter. So where it acts. So H bar acts. So the force acts at 1.861 meter below the free liquid surface. So a strong person can lift 100 kg. His weight is 9, or weight is 981 Newton, about 1 kilonewton. So the person can apply the force at a point farthest from the hinge. So the hinge is there, so we can apply the force here so that the force required can be minimized. So for maximum effect and generate a moment of 1 kilonewton meter, the resulting hydrostatic force acts under the midpoint of the door and thus a distance of 0.5 meter from the hinges. So this generates a moment of 50.6 kilonewton meter. So that is the maximum moment that person can generate, which is about 50 times the moment the driver can possibly generate. Therefore, it is impossible for the driver to open the door of this particular car because force required at this particular that is 101.239 kilonewton. The driver's best bet is to let some water in by rolling the window down a little, for example, and to keep his or her head close to the ceiling. The driver should be able to open the door shortly before the car is filled with the water, since at the point the pressure on both sides of the door are nearly the same. The opening of the door, the water is almost as easy as opening it in the air. So this is the tactics from escaping from the car. So this is a practical situation. So how we can apply the knowledge of fluid statics in practical case also. This is the best example for the same. So even the numerical, and this is the way you should think. So while solving the numerical, it should be you can consider some practical cases and apply there your theory. Then and then it will be useful actually the POs are addressed. That is actual outcome of the engineering. This is a best practical example where in this particular case it is not possible for the driver to open the door. The force required is 50 times greater than the person can exert. The best way to allow some water inside the car, and then when the forces are equalized, then we can open the door. There are equal forces on both sides, then the person can push that door as well. This is the first example where we can see the actual real situation is converted into the vertical plane surface. The second example, that is a 200 kg, 5 meter wide rectangular gate as shown in figure. So this is a rectangular gate. Generally, most of the dams, such kind of gates are provided to release the water from the dam, especially in flood conditions. If the dam is full with the water, then some water needs to release, or even in some cases where there's a scarcity of water uh, downstream, then also the water needs to be released from the dam. That's why the gates are provided in the dam structures. So we have we have seen some photographs earlier during the practical application of this. So this is 200 kg, 5 meter wide. Wide means it is a perpendicular to the board, rectangular gate, as shown in figure. Is hinge at B, so hinge is at B and leans against the floor. So this leans against the floor at A. So it opens like this, making an angle of 45-degree with the horizontal. The gate is to be opened from its lower edge by applying a normal force at its center. So we apply the force here. Uh, the gate opens and the water is released from this side. Determine the minimum force required to open the water gate. So in this case, we have to calculate what should be the force required here. So obviously, what is the force required by the water? That is the force exerted by the water on the surface on this side. So that much force, opposite force is required from this side. So here the x bar value, that is the center of, is exactly the 1.5 meter. And h bar, the which is applied. So this is h bar. X bar is the distance of CG from free liquid surface, and h bar is the distance of CP from the free liquid surface. Now again, this is an inclined plane surface, so use the expression here f is equal to gamma a x bar. So one thing you remember, whenever there is a numerical on hydrostatic surfaces, so two expressions are must. So even though you cannot solve the numerical, so only writing the two expressions will give you at least 2 marks. That is expression of f and expression of h bar. Only appropriate expressions required. F equation is common for all three cases except curved surface, but the h bar expression varies. So at least one can do that thing, even maybe because of the time constraint. If you are unable to solve the numerical, in that case, only write the expressions and leave it. Then at least you can get 1 or 2 marks there. So this is the expression of f, that is gamma a x bar. So that is force. Now recognize the expression parameters here. So obviously it is in water. So gamma is 9810 Newton per meter square. Area of the gate. So this is 3 meter. So sine 45 is equal to 3 upon distance. So we require this side. So that is 3 upon sine 45. That gives this side. So area is nothing but it is the inclined plane surface. So this side, which is 3 upon sine 45, and perpendicular to the plane, that is 5 meter. So this is perpendicular to the plane. So 5 into this, that is 9.24 meters square. So that is the area of the inclined plane surface. X bar is the distance of CG from the free liquid surface. So obviously this is 0.5 meter, and midpoint of so midpoint of this is 1.5. So around 2 meters. So by putting all these values, we can calculate F. So F is 181.34 kilometer. Secondly, H bar, as this is the inclined plane surface, the expression of H bar, that is its distance from free liquid surface, is Ig sine square theta upon Ax bar plus X bar. Already in this, only we have to determine Ig, as it is a rectangle, because sine theta take care of the inclinations. So it is we can use the expression of rectangle. So if we consider this as a rectangle, the side parallel to the surface, so Ig is 1 by 12 BD cube. Now we have to recognize which is B, which is D. So always the side which is parallel to the free liquid surface, so that is which is perpendicular to the board or perpendicular to the plane, that side is parallel to the free liquid surface, so that is 5 meters. And D, which is perpendicular, that is 3 by sine 45. So by putting the values, we can calculate Ig, that is 31.81 meters. So that is the crux. How to recognize B and D, I once again tell you. So B is nothing but the side which is parallel to the free liquid surface. So in this case, it is 5 meters. And perpendicular is 3 upon uh, sine 45. That is a perpendicular. This particular perpendicular. So 31.81 m raised to 4. And H bar is 2.861 meter. So this is the force where it applied. Somewhere here, it's the force is applied. Now, if we see the free body diagram, so this is a plane, a reference plane, we can say. This is actual gate. So this force we require to calculate, that is what force is required to open the gate. So X, that is this distance, we have to calculate where the force is acting. So whatever the H bar, so uh, that H bar is equal to also X is nothing but a distance. So this angle is right. So this is our H bar. So again, sine theta is equal to H bar upon X. So X is equal to H bar upon sine 45. So it comes around 3.6. So this is where the force is acting. Then this distance is exactly at the mid. So that is Y bar. Again, we can calculate Y by using the expression. So comes is 2.12. So weight of the gate also plays important role, because weight is given which acts at the center, and it is acting downward, that is W. So this 200 kg converted into kilonewton, that is 1.962 kilonewton. So this is the free body diagram. Now applying the moment about hinge, you can say about hinge. So F into X. So this F into X plus W, this is in the anti-clockwise direction. So plus W, this component is a cost component, which is W cos 45 into Y. That is equal to, this is opposite side, that force required, that is FR into Y. Where X we have already calculated, that is H bar upon sine 45. By considering the trigonometry here, this trigonometry, because this is H, this is H and X. So if we consider this triangle, so sine 45, that is equal to H bar upon X. So X is equal to H bar upon sine 45. That comes X value. Similarly, we can apply this for Y also. And so the force required after footing, the force required is 86.9 98 kilonewton. So we have to apply the force at the center. So this is 286.98 kilonewton. If we apply at the center, so that much force is required. This is at the center. So, but the minimum force required. So, if at the center it is so, if minimum force required, if we apply the force at A, if the force is applied at A, so obviously the moment required or force required is more because the distance increases twice. So the force is reduced to half. So exactly half of this. So the minimum force required at the bottom, that is 143.98 kilonewton. So if we apply the force here, obviously it's force required. So this y distance is exactly double. So instead of 2.12, it is exactly double. So the value of force is reduced by half. So instead of 286.96, it reduces to half. That is 143.98. So this is a minimum force required at the bottom, but uh, uh, here the mechanism is provided to apply the force that is at its center. It is recommended if you provide the mechanism here, the force required is almost reduced by half. So this is engineering mechanic principles. So it is applied for the dam gate opening. So accordingly, the mechanism is provided accordingly the force is applied there with the help of some rope pulley arrangement to open such kind of gates. So this is another practical example which is generally applied in the dam area. So even in the construction of dam wall also, these principles are used. So depending on where to, that's why the dam thickness is highest at the bottom, and as we go up, this thickness decreases, so that it can sustain that particular force because the pressure at the bottom is maximum. This is second example. So this is on inclined plane surface. So earlier one was the vertical plane surface. Now the third example again on the gate. So here the 3 meter high uh, and 6 meter wide rectangular gate. So this is a rectangular gate. Is hinged at the top edge at A and is restrained by a fixed ridge at B. The ridge is provided so that the gate remains closed. Determine the hydrostatic force exerted on the gate by the 5 meter high water. Total height is 5 meters. So the gate is 3 meters. So the total height of the water in this side is given, and the location of pressure center. So hydrostatic force exerted by the water is, so this hinge is provided. So whether what should be the force required at this hinge to keep the gate or to open that particular gate. So again, this is vertical plane surface. So F is equal to gamma A x bar. So the values of gamma as it is water 9810. Area, it is a rectangle gate. So 3 meter is the height and 6 meter is the width. So which is perpendicular to board. So as a area of rectangle 3 into 6. X bar is 2 meter plus half of this 1.5, that is 3.5 meters. So you can calculate this is a hydrostatic force exerted on gate. And its point of application we can calculate by using this. H bar is equal to Ig upon X bar plus X bar. So again, in this case, the B value is parallel to the free liquid surface, which is 6 meter. So this is B value, and 3 is the height. That is 3 meter is D. So it is 1 by 12, 6 into 3 cube. So it comes around 13.5 meter raised to 4. So bar value, that is point of application of this force, which is 3.74 from the free liquid surface. So the hydrostatic force exerted on the gate is this, so, and its location is 3.714 meter from the free liquid surface. So here the hydrostatic. So in order to open this particular gate, again like previous problem, if we have to apply at the same location, almost this much force is required. If we apply it here, slightly the force required is less. So generally at the bottom, it is always recommended. Third case, now the consider gate as shown to be a quarter circle. So the curved gate, and most of the practical cases, the curved gates are used. Quarter circle of radius of this, it is given that is 8 meters. So this much is the radius is 80 centimeter with hinge at 8 meter. So this hinge is at 8 meter below the free liquid surface. 8 meter below the free liquid surface, as shown in figure. If the gate is 1 meter wide, so the width of the gate, so here is the curved surface. You can say this width of the gate is, which is perpendicular to the board, like this. That is 1 meter. What force P is needed to hold the gate in the position shown? So what force is required P for this hold the gate as it is in the diagram? So also keep the gate closed. So hinge is provided at the bottom here. So because of the water pressure, the gate opens, and in order to keep the gate closed, some force is required at the opposite side. So that force needs to be calculated. Now let's move the forces. If you consider the forces FH and FV to the center of the circular arc, as shown in figure. So this is the center of the circular arc. This is allowed since all the infinitesimal force components that make up the resultant vector force, Fh plus Fv, pass through the center of the arc. So here all the forces acting. So the component of the forces, that horizontal component is Fh, vertical component is Fv. So there it acts. The force that act on the gate are displayed if the moments are taken about the hinge. The force affects, which is at the hinge, then Fy and Fv. These forces produce no momentum because if we apply the moment about hinge, so all this all these forces acts there. So Fh and Fx, Fy and Fv. So all three forces are passing through hinge. So it doesn't create or they do not create any moment, because if we take the moment about hinge, then only force, that is Fh, it creates a moment. So Fh is obviously equal to P. So we have to calculate only horizontal component in this case. So P is equal to Fh. The force P is equal to Fh. So Fh is the horizontal component. So that we can calculate, that is horizontal component. So the force acting on the projected area of the curved surface on the vertical plane. So if we take a projection of this curved surface on vertical plane, so it becomes a rectangle. So Fh is equal to gamma A x bar. So again, as it is submerged in water, so gamma is 9810. Area of the projection. So this is its height is 8 meter because its radius is 8 centimeter. So it's 0.8 meter. And width, which is perpendicular, that is 1 meter, it is given. The gate is 1 meter. So it's, if we take the projection of this curved gate, it becomes a rectangle of size 0.8 into 1 meter. So area comes around 0.8 meters square. So X bar is exactly the mid of this. So it is 0.8 meters. So midpoint is 0.4. The hinge is at a distance 0.8 meter from free liquid surface. So 8 minus 0.4, that gives us X bar. So X bar value is 7.6 meter. So all three values known to us. So we can calculate FH. So this much force is required. That is 59.645 kilonewton force is required here to keep the gate closed. This way you can make the numerical simple. Always solving this numerical or hydrostatic forces. Remember one thing, write the expressions, recognize the quantities given in the numerical. As far as possible from the statement, diagram is essential. So because most of the parameters we can calculate from the diagram because the trigonometry is involved here. So this way we can make the any complicated problem even simple. So this is even a curved surface. We do not require the end resultant force because the force which creates moment, that is a horizontal component of the resultant. So only horizontal component is considered here. And the same because the distance of FH and P are same from the hinge. So whatever the FH value, same is the value of P. So this much force is required. That's it from this particular session. So there are a number of numericals there, but again, we can use the same expressions. Only understanding of the statement, uh, drawing appropriate diagram or orientation of the surfaces, then use a trigonometry to calculate the various forces, moment. So most of the engineering mechanics knowledge is also required while solving problems. So for practice, you can take book numerical and solve using these methods only. So writing the expression, write the given quantities in appropriate notations, and put the values and solve. Only three quantities to be determined, either the hydrostatic forces on surfaces, that is F, then its distance from the free liquid surface, that is point of application, that is Cp. And in some cases, the force required at the opposite side by taking moment. About some point, generally the moment is taken about hinge. So that way we can calculate as per the given information. So nothing difficult in that. If you have a good engineering mechanic principles, you can easily solve or you would like to solve such kind of problems. For practice, you can refer any book and only take the statements. Don't copy the methodology because every book has different methodologies and different concepts. So that may create the confusion. Avoid that. So only take the statement and solve by using this particular principle. That's it. At the end of this particular session, you should be able to apply the expressions of total pressure and the center of pressure for solving numerical and submerged surfaces. So all four cases we have covered in this session. That is vertical plane surface, inclined plane surface, and the curved surface. As far as horizontal plane surface is concerned, that there is no such numerical because there is no complications there. So horizontal plane surface because directly the depth of water from that vertical plane surface that gives us X bar. So we can calculate and H bar that is equal to X bar. So there is no complications in horizontal plane surfaces. Thank you very much.